And so we're going to start off with a talk from Ziteng related to a paper from OOPSLA’25. And he's going to tell us a little bit about how we can use homomorphisms to better understand our code. Please.
Thank you, Pavel, for the introduction. Can you guys hear me? OK, great. OK. Hi, everyone. My name is Ziteng Wang, and from UT Austin. Today, I'm going to present our work, Homomorphism Calculus for User-Defined Aggregations. A little bit context here. So modern analytics run on frameworks like Apache Flink and Spark that aggregates massive tabular data. People call them data frames. And then there are two basically operations you can choose from. The first one is built-in aggregations. They are basically a set of standard operations, very handy to use and also highly optimized. On the other hand, there are also user-defined aggregations. That's the place where the developer can express their own domain-specific logic, such as custom statistics or telemetry summaries. And nowadays, user-defined aggregate functions are everywhere in the large-scale analytics. So how do we implement such custom aggregation logic here? Well, essentially, UDAFs are just a fold here. That means that it consists of two parts. The first part is the initial state, which is the state you will have at the beginning of the computation. It also has the so-called accumulate function, which basically takes in the current state and the current input, and then it will force the next row as the input into the state. If you expand the definition of fold, that will be the form that we all familiar with here. So to implement a UDAF, init plus accumulate function are like the minimum things you need. But most of the time, the UDAF also includes a merge function, as both Spark and Flink supports, that basically allows parallelization and incrementalization. This merge operator takes two intermediate state buffer results, B1 and B2 shown here, and then it will combine them and produce a new result state buffer. To see the main action, let's first take a look at the incremental computation. Imagine that you have some chunk of data that you already processed, and you already have the result through running the UDAF computation. And then you have some newly arrived data such that you wanted to compute the new output by, well, combining the old data and the new data frame. The problem is that the input data you already processed might be a large data frame, and you don't certainly want to repeat the work you've already done here. So instead of running the computation again, we just run the aggregation on the newly arrived data and get the partial state. And using the merge operator, we were able to merge the previous state with the new state and get the final result. For the case of parallel computation, the input is partitioned into different shards that get processed over multiple nodes. And then each node will have their own intermediate result. And this result state buffer will be repetitively processed by using the merge operator to get the final result. We saw now merge functions are useful, but what does it mean for the merge to be cracked? Well, basically, it needs to satisfy this algebraic law I show here. Here, it says that the UDAF computation P is the data frame homomorphism if there exists a merge operator such that, well, for all of the data frames D1 and D2, the result of running UDAF on the D1 concatenates with D2 should be equivalent to the result of first individually run the aggregation over two data frames and then use the merge operator to combine them. On the other hand, if the correctness condition isn't satisfied, well, bad thing can happen. Here, the wrong merge function will corrupt the result. As an example, let's consider if the merge output depends on how data was processed and merged. In that case, if the order of how you merge data is dependent for the output, then this will introduce non-determinism in your computation. That means depending on the order, like you are merging the intermediate state buffer, that give you like a different output. In distributed execution, we don't have control over how the order, like all the intermediate state buffers are merged. In that case, that might give you incorrect output. And we know that developers write these merge functions by hand, so it's very easy to get wrong. In fact, in our evaluation, we collected 45 UDF functions from GitHub, and we did find 9 out of 45 of them has bug. Okay, and what makes the problem even worse is that the merge function does not always exist. Let me show you this example. So this simplified UDF basically aggregates on the events from a website that is tracking all of the user clicking and all of the events. And if you take a look at the third line, it basically says that if the current event is checkout, then you update checkout count to be event count. Well, can a merge function exist for this UDF? Well, the problem is that, as you might already noticed, checkout count snapshots event count at checkout event. So every time it's just override the checkout count. And there's no way you can recover the previous checkout count at a time we are merging them. So searching for a merge is basically futile here. You will waste time searching for something that doesn't exist. So in this work, we wanted to solve this problem. Given a UDF-P, we wanted to see that if the UDF-P is the data frame homomorphism, then we wanted to synthesize a merge operator that serves as the witness of the homomorphism property. On the other hand, if P is not a data frame homomorphism, we want to prove that no merge function exists, and we will warn the user that if they write any merge operator, that is unsafe. Either way, the developer gets a trustworthy answer so that we can better assist them in writing custom aggregations. So what are the challenges here? Well, to synthesize merge, we need to first verify the correctness given a merge function. Let me tell you, this is the challenging relational verification problem because of the following reasons. First, as you might notice, this property as a specification involves universal quantification over all data frames. And secondly, the specification includes the reasoning over concatenation of arbitrary data frames, which may have, you need to reason more semantics or concatenation here. And finally, the UDF computation itself here, P, is unbounded over the input data frame. So this makes a really challenging relational verification problem. Our solution to this problem is the introduction of normalizer, which reduces verification to a local per-row property rather than reasoning the arbitrary data frames. This is based on the observation that accumulate function f needs to satisfy a generalized commutativity condition with respect to the merge operator O+. Let me tell you more about generalized commutativity here. We call this commutativity generalized because it relates to functions of different input parameters. Here, B1 and B2 are two intermediate state buffers, and then we first sequence them into the merge function. The output now will be sequenced into the accumulate function, where the other input is the current row R. This will be equivalent to the alternative execution path where we first do accumulation on B2 and R, and then use merge function to merge the, partial result from B1. As you can see here, none of the tau R and tau here are, the type of data frame. So we are not reasoning about data frames here. Instead, we are reasoning about the input per row and the state buffer. The key result here we have is fold is a homomorphism if and only if the accumulate function satisfies those properties I showed here. And I started to introduce the second condition, which is the identity law. This is the side condition that basically states that merging the empty partition does nothing instead of changing the result. Cool. So now that we have a local way of verifying, this also makes synthesis problem simpler. This is based on the result A UDAF is homomorphism if and only if its accumulator function f has a normalizer h, and the normalizer is the merge operator. So instead of finding the merge operator, we can just find the normalizer function h with respect to the accumulator function f. Now, the most natural thing to think about is, well, we can probably use some off-the-shelf Saiga solver for normalizer synthesis now that we have this tractable per row synthesis spec. But we have two problems here. First, the search space for Saigas could explode when the state has many fields and nested collection, as in this example. And secondly, searching for a non-existent merge operator never terminates. So we may waste a lot of time and didn't get the result of warning the developer that this UDF isn't homomorphism. So we designed our tool inc such that it will take an input UDF-P, and then it will use a series of proof rules to refute the existence of merge function at first. And then to make synthesis tractable, we use type-directed decomposition to break down the synthesis problem into simple subproblems. Let me start with the first idea. The first idea is the proof rules for refutation. We want to reject hopeless problems before synthesis. And we design a series of necessary conditions. As an example, here is the condition we're using to showcase. So this basically says that the condition where the cumulative function is inconsistent to support a merge operator. Let me explain this in detail. It says that there exists a state buffer S and the input X, such that if you apply the cumulative function on this initial state I, then it preserves the initial value the same. But if you apply this on another state S, then state does change on this accumulative function. That means that the order or like the current state you are applying does affect how the cumulative function will update the result. So this accumulative function is inconsistent. There's no normalizer for it. And now we are able to synthesize, but synthesis is still hard. That's why we are using our second idea, type-directed decomposition. This is based on the following observations. First, UDFs are often made of multiple smaller operations combined. And second, a normalizer for a composite type split into smaller normalizers. What's even better is that solving smaller normalizer, the problem of solving smaller normalizers are independent to each other. So naturally here, we'll be able to decompose normalizer synthesis to independently solvable subproblems. Here's an example to see that in action. Here's the normalizer state we just seen in the previous slide, and it is made of 3 items. The first 2 are scalar values, integers, and the third one is a map of just a collection. Here, our type-based, type-directed decomposition is able to decompose the problem of synthesizing the normalizer into different scalar leaves problems. That is what the green boxes are highlighting, H1, H2, and H3. And then we can use inductive synthesizer to find the normalizer for the scalar leaves. On the other hand, once we have these scalar leaves, we're able to use derivation rules to instantiate larger or more complicated normalizer from those leaf normalizers. For example, H4 is instantiated from H3, and H1, 2, and 4 can make together to have the normalizer for the root normalizer here. So here we are searching only the scalar leaves, and everything else was derived structural. To recap, we have 3 key ideas here in our work. The first one is we reduce the synthesis and verification problem from using the full dataframe property to a local per row property. And secondly, we designed the proof rules for refuting homomorphisms. And finally, we use type-directed decomposition to make synthesis scalable. In the paper, we give a homomorphism calculus that captures the 3 key ideas. For the evaluation, we collected 50 tasks from GitHub, and 45 of them are homomorphic, meaning there exists a merge function for them, and 5 of them are non-homomorphic. Interestingly, all of the UDFs comes with developer-written merge function, but we know that 5 of them actually Well, they are non-homomorphic, meaning that the developer-written merge function is necessarily buggy. And forgot to mention, these tasks are either Apache Spark or Flink UDAF implementations. So our prototype tool, incr, was able to synthesize 43 out of 45 merge operators. It is able to successfully refute all of the non-homomorphic benchmarks and significantly outperforms the existing synthesis baselines. For the ablation study, we evaluated whether our key contributions in merge synthesis synthesis are significant for the success of incr. And the evaluation result says that all of them are key to the success of our tool, incr. For refutation, we turn off all of the refutation rules, and we just rely on CVC5 SIGA solver to report the problem is infeasible. But that one can only refute 2 out of 5 non-homomorphic benchmarks. So that's all for incr. I'm excited to share our work with you today, and I'm happy to take questions.
Right, well, so let's take questions at the 2 microphones. And if you wouldn't mind saying your name and affiliation.
Okay. Hi, it's Caleb Stanford, UC Davis. Thank you very much for the very nice talk. So in practice, developers do write merge functions and reduce functions that are not necessarily deterministic, sometimes non-deterministic. For example, things like an argmin or an argmax is a good example, where maybe I don't really care which minimum I return as long as it's one of the minimum elements. I was wondering if your techniques to synthesize merge function or determine if it's possible would generalize to this non-deterministic or non-functional setting.
I think it does generalize to this particular setting. So if I understand correctly, you are saying some particular value are not necessarily required to satisfy this property. In that case, I think the developer will be able to extend our prototype tool to ignore certain fields and only say like this is particular field that we care about, and the other non-deterministic things will be ignored. Is that what you're asking?
It's probably a little bit more general than that, but that may handle some cases. Or we could also take it offline.
Okay.
Yeah, but thank you for the nice work.
Yeah, thank you.
Hello, I am James Zheng from Stanford. First of all, thank you for the talk. It was very interesting. And so my question is, it seems that you are unconditionally decomposing your result type into scalars, but what about for accumulation functions that necessarily operate on multiple fields at a time, right? It seems that would impact completeness, and also like, do you have any argument for completeness or no?
That's a really great question. In our paper, our rule for decomposition, it does support the case where you have dependencies between all of the fields. In that case, my answer is no, you cannot decompose them. So right, this example we present here is really like a simplified version, but I agree, like in that case, we can just decompose whatever we can, but leave the undecomposable part behind.
Thank you.
Yeah.